There is something drifting through space right now. It has no crew, it makes no sound, it does not know where it is going, and it cannot turn around. It is smaller than a car, older than most people alive today, and it is the farthest object that human hands have ever built and sent into the universe. Right now, as you listen to this, it is moving, quietly, steadily, through a darkness so complete and so vast that even the concept of empty begins to feel inadequate. And the strange and beautiful thing is that it has been doing this, without stopping, without rest, without a single moment of hesitation, for nearly half a century. This is the story of Voyager 1, but it is not really a story about a spacecraft. It is a story about time, about distance, about the quiet enormity of the universe we live in, and about what it means that we as a species chose to reach into it. It is a story that asks a question so simple it almost sounds like a child asked it, and yet so deep that scientists spend entire careers trying to answer it. Where will Voyager 1 be in 1 million years? Let that question sit for a moment. 1 million years. It is a number we say easily, the way we might say 1,000 or 100. But 1 million years ago, our ancestors were not building cities or writing languages. They were not lighting fires in organized communities or telling stories the way we tell them now. The world looked recognizably similar, the oceans were in roughly the same places, the mountains existed, but the creatures walking on the land were different versions of what we would eventually become. 1 million years is not just a long time, it is a different world. And into that incomprehensible stretch of future, we have already sent something. It left the ground in 1977, and it is not coming back. There is something quietly emotional about that if you sit with it long enough. We built a machine, a modest little machine by today's standards, and we gave it just enough speed to escape the pull of everything we have ever known. And then we let it go. And it went. And it has never stopped going. Every single day, Voyager 1 travels about 1.5 million kilometers further from Earth. Every day, without fail. Through regions of space where there are no landmarks, no mile markers, no way to even feel that movement is happening at all. It just keeps going, like a thought that was released into the universe and can never be recalled. To understand where Voyager 1 will be in 1 million years, we first need to understand what it is, where it came from, and what it has already passed through. Because the journey so far is already remarkable enough to make the future feel both wondrous and slightly dizzying. And that feeling, that slow, quiet dizziness of realizing how large everything really is what this story is really about. Voyager 1 was born in a very specific moment of human history. The 1970s were a time when space exploration still felt new, when the moon landings were fresh in people's memories, and when a certain generation of scientists and engineers believed, with genuine conviction, that the universe was something humanity was just beginning to reach into. NASA was ambitious in those years. Not recklessly so, but with a kind of careful, methodical boldness that produced some of the most extraordinary achievements in the history of the species. And one of those achievements was a mission that, at first glance, seemed relatively modest. Send 2 spacecraft past Jupiter and Saturn, gather some data, take some photographs, and learn something about the outer solar system. That was the original plan. Study the gas giants, measure their magnetic fields, map their moons. It was scientifically important work, but it had a beginning, a middle, and an expected end. The spacecraft would do their job, the data would be collected, and eventually the machines would fall silent as their power sources drained. That was the plan. But the universe, as it so often does, had something else in mind. Because what the scientists building Voyager 1 realized, with growing excitement, was that the alignment of the outer planets in the late 1970s created what they called a grand tour opportunity, a rare configuration that only happens once every 175 years or so, where Jupiter, Saturn, Uranus, and Neptune are positioned in a way that allows a spacecraft to use the gravity of each planet to slingshot itself toward the next one, like a stone skipping across a series of ponds, gaining speed with each skip. This gravitational assist technique, which sounds almost like something from science fiction when you first hear it, is completely real and rooted in deeply understood physics. When a spacecraft passes close to a planet, the planet's gravity pulls on it, accelerating it and curving its path. If the geometry is right, the spacecraft can steal a tiny amount of the planet's orbital energy, gaining speed without burning any fuel. It is not magic, it is conservation of momentum applied on a planetary scale. And in the late 1970s, The planets aligned in a way that made this possible, in a way that would not come again for generations. The scientists called it a once in 1.75 years opportunity, and they took it. So Voyager 1 was launched on September 5th, 1977, about 2 weeks after its twin, Voyager 2. The slightly counterintuitive naming Voyager 1 Launch Second came from the fact that Voyager 1 was placed on a faster trajectory, one that would allow it to overtake its twin and reach Jupiter first. From the moment it left the launch pad in Florida, it was already moving faster than almost anything humanity had ever created. Rockets provided the initial push, but it was the careful mathematics of orbital mechanics and planetary gravity that would carry it truly far. The spacecraft itself was not especially large. It weighed about 825 kilograms, roughly the weight of a small car. Its antenna, the large dish-shaped structure used to send and receive signals from Earth, was about 3.7 meters across. Its instruments were designed to measure magnetic fields, cosmic rays, plasma waves, and the properties of the space it moved through. There were cameras, though they would later be turned off to conserve power. There were instruments for studying charged particles and the solar wind. Everything was chosen with care, with the understanding that once the spacecraft left, there was no sending a technician to fix anything. Whatever went up had to work, or the mission would simply fail in silence, billions of kilometers away. And then there was the golden record. This was not a scientific instrument in the traditional sense. It would not measure magnetic fields or count cosmic rays. It was something else entirely. It was a message, a copper disc, plated in gold to protect it from the corrosion of time, containing sounds and images and music and greetings from a planet called Earth. The sounds of rain, of ocean waves, of wind through trees, the calls of birds and whales, the sound of a mother kissing a child, music from multiple human cultures, from a bark prelude to a Navajo chant to Chuck Berry's Johnny B. Good. Greetings, in 55 languages, a diagram showing where Earth is located relative to pulsars, those rapidly spinning neutron stars whose timing is as precise as any clock, so that whoever found the record could, theoretically, calculate where it came from. The golden record was not placed on Voyager 1 because anyone seriously expected it to be found. The odds of any intelligent civilization ever intercepting a single spacecraft drifting through the void of interstellar space are, by any honest calculation, extremely small. The scientists knew this, but they included it anyway because the act of including it said something important. It said that we are the kind of species that, when we send something into the unknown, feels the need to introduce ourselves. That even when no one is likely listening, we still want to speak. The record was less a practical message than a statement of character. And that, in its own quiet way, is one of the most human things about this entire mission. Voyager 1 flew past Jupiter in March of 1979. The images it sent back were stunning. Jupiter is not just a big ball of gas. It is a turbulent, dynamic, storm-swept world of breathtaking scale, with cloud bands stretching across its surface in shades of orange and white and brown, and its great red spot, a storm so large that Earth could fit inside it, swirling with an energy that had persisted for centuries. Voyager 1's cameras revealed details that had never been seen before. They showed active volcanoes on Jupiter's moon Io, making it the first world beyond Earth ever observed to have ongoing volcanic eruptions. They revealed the thin, faint ring system around Jupiter, not as famous as Saturn's but just as real. They showed the strange, fractured terrain of the moon Europa, hinting at something remarkable beneath the surface. A global ocean of liquid water hidden under a shell of ice, a discovery that would eventually inspire a whole branch of scientific speculation about life in unexpected places. From Jupiter, Voyager 1 swept onward towards Saturn, arriving in November of 1980. Saturn was its final planetary target, the last world it would study up close. And what it found there was equally extraordinary. The rings of Saturn, seen up close for the first time with this level of clarity, turned out to be far more complex than anyone had imagined. What looked from Earth like a few broad bands resolved into thousands of individual ringlets, braided and clumped and sculpted by the gravitational influences of Saturn's many moons. The moon Titan was revealed to have a thick atmosphere, a mysterious orange haze of nitrogen and organic molecules, hinting at a chemistry that scientists are still studying today. And then, after Saturn, Voyager 1's cameras looked back at the solar system one last time, and what they captured became one of the most quietly affecting images in the history of photography. In 1990, at the request of the astronomer Carl Sagan, Voyager 1 turned its cameras back toward the inner solar system and took a family portrait. From a distance of about 6 billion kilometers, it photographed the planets one by one. Earth appeared in the image as a tiny point of light, barely distinguishable from the scattered light of the sun, a small blue dot suspended in a ray of sunlight. Sagan wrote about that image in words that have been quoted many times since, and yet never seem to lose their weight. He described Earth as a mote of dust suspended in a sunbeam, and noted that everything humanity had ever known, every king and peasant, every act of courage and cowardice, every invention and discovery, had happened on that tiny speck. It is a thought that does not get easier with repetition. It gets harder. After that photograph, the cameras were turned off permanently to save power for the instruments that still mattered. And Voyager 1 continued on its way, pointed toward the edge of the solar system, toward a boundary that scientists had long theorized about but never directly observed. A boundary that would take another 2 decades to reach. A boundary that, when crossed, would make Voyager 1 the first human-made object to truly leave the cradle we were born in and enter the wider universe beyond. That crossing, and what it means, and what lies beyond it, is where the real journey begins. Because up until that point, as extraordinary as the mission had been, Voyager 1 was still technically home. Still within the influence of the sun, still inside the vast, invisible bubble that our star creates around itself. And the moment it crossed beyond that bubble, everything changed. Not dramatically. Not with a visible flash or a sudden jolt. The universe does not announce its boundaries with signs. But in the data, in the readings from Voyager's instruments, something unmistakable shifted. And the scientists watching those readings understood that they were witnessing a first. A moment that no one who came before them in all of human history had ever been present for. There are very few firsts left in the world. Almost everywhere worth going on this planet has been visited. Almost every coastline has been mapped. Almost every mountain summit has been stood on. But the moment Voyager 1 crossed into interstellar space was a first in the deepest sense. It was the first time humanity had ever reached beyond our own solar system. Not with a human body, not yet, but with something we made. With something that carried our fingerprints and our curiosity, and in its own way, our voice. And that first happened not in a future century, not in some imagined age of advanced technology, but on August 25th, 2012, within the lifetimes of most people listening to this right now. You were alive when humanity left the solar system for the first time. It happened quietly, announced in a scientific paper, acknowledged with cautious excitement by a small community of researchers and engineers, most of them older by then, many of them having given decades of their careers to this mission. But it happened, and the spacecraft is still going, still transmitting, still sending back data from a place that no instrument had ever sampled before. And as it moves further and further from the sun, the question of where it will eventually be takes on a different kind of weight. Because we are not just asking where a probe will end up, we are asking where the first piece of humanity to enter interstellar space will find itself when 1 million years have passed, and everything we know has long since changed beyond recognition. To answer that question honestly, we need to first understand the environment Voyager 1 has entered. Because interstellar space, the space between the stars, is not simply more of what exists inside the solar system. It is something different. Something quieter and colder and stranger in its own way. And understanding what it is, and what moves through it, and how Voyager will interact with it over immense stretches of time, is the key to understanding where this quiet traveller is ultimately going. So let us slow down for a moment and take a careful look at the space that Voyager 1 has entered. Because it is not the emptiness most people imagine. It is something richer, and in its own strange way, more alive. The sun creates an enormous bubble around itself. This bubble, called the heliosphere, is generated by the solar wind, a constant stream of charged particles that flows outward from the sun in every direction at hundreds of kilometers per second. This stream of particles pushes against the material of interstellar space, carving out a region where the sun's influence dominates. Everything inside this bubble is technically within the solar system, in the sense that the sun's wind and magnetic field shape the environment. Everything outside it belongs to the galaxy in a more fundamental way, governed by forces and particles that have nothing to do with our particular star. For most of its journey, Voyager 1 was inside this bubble, moving through a solar wind environment that gradually thinned and slowed as the spacecraft moved further from the Sun. But there is a point where the solar wind slows dramatically, where it collides with the pressure of interstellar space and forms what scientists call the termination shock, a kind of bow wave where the outgoing solar material suddenly decelerates. Beyond that, there is a region called the heliosheath, a turbulent, foamy boundary zone where the solar wind material is compressed and heated. And beyond that, there is the heliopause, the true edge, the outermost boundary where the Sun's influence ends and interstellar space begins. Voyager 1 crossed the termination shock around 2004. It spent the following years moving through the heliosheath, sampling that strange transitional environment. And then, in 2012, its instruments detected the unmistakable change that marked the heliopause. The density of solar particles dropped sharply. The density of galactic cosmic rays, particles accelerated by distant supernovas and other energetic events across the Milky Way, rose just as sharply. The magnetic field orientation changed, and scientists confirmed, after months of careful analysis, that Voyager 1 had crossed into interstellar space. What Voyager 1 found there was not a vacuum in the classic sense. Interstellar space contains material, just not very much of it. On average, there is roughly 1 atom for every cubic centimetre of interstellar space. Compare that to the air in the room where you are right now, which contains approximately 27 billion molecules per cubic centimetre, and you start to get a sense of how tenuous the interstellar medium really is. It is, for all practical purposes, empty, but it is not perfectly empty. It contains hydrogen and helium, the lightest elements, left over from the Big Bang and from stellar winds. It contains traces of heavier elements, dust grains, complex molecules in some regions, and a constant bath of cosmic rays, high-energy particles travelling at close to the speed of light from sources scattered across the galaxy. This is the environment Voyager 1 is now moving through, and it will continue moving through it for a very, very long time. There is nothing to slow it down, no friction, no resistance worth mentioning. The few atoms it encounters per cubic centimetre create no meaningful drag. The spacecraft is essentially in permanent freefall, following a path governed only by the gravitational influences of distant stars and the slow, gentle pull of the galaxy itself. It will not stop. It will not decay significantly. It will not fall apart in any meaningful way on the timescale we are discussing. It will simply drift, for 1 million years, through the quiet immensity of interstellar space, carrying its golden record and its silent instruments and its small cargo of human ambition, until even the concept of where it started begins to lose its meaning. That drift, and all of the remarkable things it will carry Voyager 1 past and through and around, is what the rest of this story is about. We are just getting started. There is a particular kind of confusion that happens when you try to think about the scale of space. It is not the confusion of complexity, the kind you feel when you try to understand a difficult equation or follow a dense argument. It is something gentler than that, and in some ways more unsettling. It is the confusion of simply not having the right mental equipment. Human brains evolved to navigate a world measured in meters and kilometers. We can feel the difference between a short walk and a long one. We can understand, in a bodily way, what it means to drive across a country or fly across an ocean. But when the distances involved are measured in light years, something in our comprehension quietly breaks down. We say the numbers, we do the arithmetic, and then we sit with the results and feel a kind of gentle vertigo that does not go away. Understanding where Voyager 1 will be in 1 million years requires sitting with that vertigo, not fighting it, but letting it wash over you like a slow tide. Because the distances involved are not just large, they are large in a way that makes largeness itself feel inadequate as a concept. And the only way to really feel that is to start small, with something familiar, and then expand outward until the familiar becomes unrecognizable. Start with your own neighborhood. Walk outside and look at the sky on a clear night. The stars you see with your naked eye are, most of them, relatively nearby by galactic standards. The brightest ones, the ones that form the familiar constellations, are generally between a few dozen and a few hundred light-years away. A light-year, just to anchor the number, is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In 1 year, light covers roughly 9.5 trillion kilometers. That is a distance so large that if you drove it in a car at highway speed, without stopping, it would take you about 1 billion years. And that is just 1 light-year. Voyager 1 is currently just over 23 light hours from Earth. That is not 23 light years. It is 23 light hours, meaning it takes light about 23 hours to travel from Voyager to Earth. In actual distance, that is roughly 25 billion kilometers. A number that sounds enormous, and by human standards, absolutely is. If you lined up every person who has ever lived, end to end, you would not come close to spanning that distance. And yet, in terms of the distance to the nearest star, Voyager 1 has barely moved. The nearest stellar system, Alpha Centauri, is about 4.37 light-years away. Even at its current speed of roughly 17 kilometers per second, Voyager 1 would take approximately 75,000 years to cover that distance, and it is not even heading in that direction. Let that sit for a moment. 75,000 years to reach the nearest star. The first anatomically modern humans appear in the fossil record roughly 300,000 years ago. The earliest cave paintings are about 45,000 years old. Written language is around 5,000 years old. All of recorded history, everything we know about ancient Egypt and Greece and Rome and China, and every civilization that has risen and fallen on this planet, fits inside 5,000 years. Voyager 1 would need 15 times that entire span of recorded human history just to reach the closest star. And it is not even aimed there. This is the scale problem. It is not just that space is big, it is that space is big in a way that makes our fastest spacecraft feel, when measured honestly against the distances involved, almost heartbreakingly slow. And yet, Voyager 1 is moving. It is genuinely moving through interstellar space, farther from Earth than anything we have ever sent. And over 1 million years, that movement accumulates into something, not into something that crosses the galaxy or reaches another star system in a meaningful way, but into a distance that is, by any human measure, truly staggering. To appreciate what 1 million years of travel at Voyager's speed actually produces, it helps to understand exactly how fast the spacecraft is moving, and why it will maintain that speed indefinitely. Voyager 1 is currently traveling at approximately 17 kilometers per second relative to the Sun. This sounds very fast, and by the standards of anything we interact with in daily life, it is extraordinarily fast. A bullet fired from a rifle travels at roughly 1 kilometer per second. Voyager 1 is moving at 17 times that speed, continuously, day and night, year after year. Sound, by contrast, moves at about 340 meters per second in air, making Voyager 150 times faster than sound. But light moves at 300,000 kilometers per second, making Voyager 1 roughly 17,000 times slower than light. The reason Voyager 1 will maintain this speed indefinitely, or something very close to it, comes down to one of the most fundamental ideas in physics. In the absence of external forces, a moving object keeps moving. This is Newton's first law of motion, and in the environment of interstellar space, it applies almost perfectly. There is no air resistance. There is no friction against any surface. The tiny amount of material in interstellar space, that 1 atom per cubic centimeter, exerts so little drag on the spacecraft that it is essentially unmeasurable over any human timescale. The gravitational influences of distant stars will gently curve Voyager's path over millions of years, but they will not stop it. Nothing will stop it. Not in 1 million years. Not in 10 million. Not, realistically, for billions of years. The spacecraft will simply keep going, at roughly its current speed, through the quiet dark of the interstellar medium until some extraordinarily unlikely encounter changes its path. So if we multiply 17 kilometers per second by the number of seconds in 1 million years, we get a number. A large number. Roughly 540 trillion kilometers, or about 57 light years. That is where Voyager 1 will be in 1 million years, approximately 57 light years from where it started. Some calculations put the figure slightly lower, around 40 to 50 light years, depending on the gravitational influences encountered along the way, but the order of magnitude is clear. 50-some light years, in 1 million years of continuous travel. And here is where the scale problem reasserts itself with quiet force. The Milky Way galaxy, the galaxy we live in, is roughly 100,000 light years across. The distance from one edge to the other, measured through the central bulge, is 100,000 light years. Voyager 1, in 1 million years of travel, will have covered about 57 of those light years. That is roughly 0.057% of the galaxy's diameter. In percentage terms, It is as if the spacecraft had not moved at all. If you drew the Milky Way on a piece of paper that was 1 meter across, Voyager 1's million-year journey would cover about 0.5 millimeter. On that scale, you would need a magnifying glass to see it. But here is the thing about that comparison. It can make the journey feel insignificant, and that would be the wrong conclusion. Because the 57 light-years Voyager 1 will have travelled in 1 million years represents something genuinely remarkable, not in spite of the galaxy's size, but in the context of what the spacecraft is. It is a machine roughly the size of a small car, built by a species that has existed in its current form for only about 300,000 years, that has been travelling for a tiny fraction of that species' history, and that will, in 1 million years, have moved 57 light-years through interstellar space. That is extraordinary. The fact that the galaxy is even more extraordinary does not diminish it. It just places it in perspective. The neighbourhood of space that Voyager 1 will move through over the next 1 million years is not static. The stars around us are not fixed points. They move, slowly by human standards, but measurably so. Our Sun is orbiting the centre of the Milky Way at a speed of about 220 kilometers per second, taking roughly 225 million years to complete one full orbit. The stars near us are doing the same thing, each on its own slightly different orbital path, drifting past each other at speeds of tens of kilometers per second over geological timescales. What this means is that the stellar neighbourhood Voyager 1 is heading into does not look today the way it will look in 10,000 years, or 100,000 years, or 1 million years. The stars will have moved, new stars will be relatively closer, others that are close now will be farther away. The cosmic landscape is not a fixed backdrop. It is a slow, ongoing drift of countless suns, each following its own orbital path around the galaxy's centre. This means that predicting exactly where Voyager 1 will be in 1 million years is genuinely difficult, not because of any uncertainty about the spacecraft itself, but because the gravitational landscape it will pass through is complex and not perfectly mapped. We know the current positions and velocities of nearby stars with good precision, thanks to missions like the Gaia Space Telescope, which has charted the positions and motions of more than 1 billion stars with extraordinary accuracy. But over millions of years, small uncertainties in those measurements compound, and the long-term trajectory of Voyager 1 becomes increasingly approximate. What we can say with confidence is the direction Voyager 1 is heading. It is moving roughly in the direction of the constellation Ophiuchus, which lies in the general direction of the centre of the Milky Way from our perspective. The spacecraft is heading roughly upward out of the plane of the solar system, above the relatively flat disk of the galaxy in which most of the stars and gas and dust are concentrated. This is not arbitrary. The trajectory was set by the gravitational assists Voyager received from Jupiter and Saturn, which sent it flying on a specific path that happens to be directed out of the ecliptic plane. This direction has interesting implications for what Voyager 1 will encounter, or more precisely, for what it will not encounter over the coming millennia. The plane of the Milky Way is where most of the action is. That is where the gas clouds are, where new stars are forming, where the density of matter is highest. Moving above the plane, as Voyager 1 is doing, means the spacecraft is heading into a somewhat quieter region of the galaxy. A region with lower stellar density, fewer gas clouds and less of the complex, churning activity that characterizes the galactic disk. This is good news for Voyager's long-term survival. The emptier the space it travels through, the lower the chance of any meaningful collision or disruption. Now, when people hear the word collision in the context of space travel, they sometimes imagine a dramatic event, two objects crashing together with a flash and an explosion. But in interstellar space, the relevant collisions are not dramatic. They are mundane to the point of near invisibility. A dust grain, perhaps 1/1,000,000th of a meter across, travelling at a high relative velocity, striking the surface of the spacecraft. These impacts happen slowly and infrequently, and they do cause microscopic damage. Over millions of years, the accumulated effect of interstellar dust impacts will gradually erode the spacecraft's surface, pitting the metal and plastic and gold-plated surfaces of the Golden Record. But the rate of this erosion is slow enough that Voyager 1 will remain structurally intact, recognizably itself, for timescales far beyond 1 million years. There is also cosmic radiation to consider. The interstellar medium is threaded through with high-energy particles, cosmic rays, protons and heavier nuclei accelerated by supernovas and other energetic events across the galaxy. These particles will pass through the spacecraft continuously, depositing tiny amounts of energy in its materials. Over long timescales, this radiation causes gradual degradation in electronic components and organic materials. But again, the timescales involved are long. The structural metals of Voyager 1 will not be meaningfully altered by cosmic ray bombardment in 1,000,000 years. The spacecraft will look, from the outside, essentially the same as it does today, if somewhat more pitted and faded. The golden record itself, sealed in its protective cover and made of gold-plated copper, is expected to survive essentially intact for 1,000,000,000 years. 1,000,000,000 years. The Earth is about 4.5 billion years old, so the golden record is expected to survive for roughly a quarter of the age of our planet, drifting through interstellar space in good enough condition that, if found by some future intelligence with the right technology, it could theoretically still be decoded. That is a thought that takes a moment to fully absorb. We have created an object that will outlast every human institution, every language, every nation, every species of plant and animal currently alive, and possibly humanity itself, and it will still carry the sounds of whales and rain and Bach perfectly preserved waiting in the dark. But let us return to the question of scale, because there is one more comparison that is worth sitting with before we move on. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years away. In 1,000,000 years of travel at its current speed, Voyager 1 will cover 57 light-years. To reach Andromeda at that speed would require about 43 billion years, which is longer than the current age of the universe, which is only about 13.8 billion years old. The nearest large galaxy is, in practical terms, completely unreachable by Voyager 1. Not in any timescale that has meaning. The spacecraft is ours. It will always be ours, in the sense that it will always be within our galaxy, always within the neighbourhood defined by the Milky Way's gravitational embrace, for as long as the Milky Way itself exists. This is the paradox of Voyager 1. It is by any human measure the farthest thing we have ever sent anywhere. It is in interstellar space, beyond the boundary of our solar system, in territory no human instrument has ever explored, and at the same time, by the measure of the universe, it has barely moved. It is like a message in a bottle dropped into the Pacific Ocean, and after 50 years of drifting, the bottle has moved from one end of a swimming pool to the other, while the actual Pacific stretches away in every direction beyond imagining. And yet, despite all of that, despite the humbling mathematics and the vertiginous scale, there is something deeply moving about what Voyager 1 represents. Because the scale does not make the effort meaningless. It makes it human. We are a small species, on a small planet, orbiting an ordinary star in the outer reaches of an average galaxy. We have been aware of the universe around us for, in cosmic terms, an instant. And in that instant, we built a machine, figured out the mathematics of planetary gravity, aimed it carefully, and sent it beyond the edge of everything we had ever known. That is not nothing. In a universe that is almost entirely empty, almost entirely unconscious, almost entirely unaware of itself, the fact that one tiny corner of it has produced creatures curious enough and bold enough to reach outward, even knowing how far there is to go, is itself extraordinary. The scale of space does not diminish Voyager 1, it frames it. And understanding that frame, understanding the magnificent smallness of what we have done against the backdrop of what exists, is the beginning of understanding why this journey matters. The numbers are not there to make us feel insignificant. They are there to help us feel awe. And awe, when it is genuine and unhurried, is one of the most important things a mind can experience. In the next chapters, we will follow Voyager 1 into its future. We will look at the specific stellar encounters it will have, the changes in the universe it will witness from its silent perspective, and the deeper questions its journey raises about time, memory, and what it means to leave something of yourself in a universe that does not need you, but is richer for your presence. But for now, sit with the scale, let it settle, because everything that comes after makes more sense when you have truly felt how large the stage is. Somewhere deep in the spacecraft, in a chamber designed carefully to resist the cold of space, 3 small canisters contain chunks of plutonium. 238. Each canister is surrounded by thermocouples, simple devices that convert heat directly into electricity whenever there is a temperature difference between 2 points. The plutonium produces heat as it slowly decays. The thermocouples catch that heat and turn it into electrical current, and that current flows to the spacecraft's instruments and computers and transmitter, keeping everything alive. This system is called a radioisotope thermoelectric generator. It produces no moving parts, no combustion, no rotating turbines. It is quiet, reliable, and remarkably durable, and it is slowly, inevitably, running down. Plutonium, 238 decays with a half-life of about 87.7 years. This means that every 87.7 years, the amount of plutonium remaining in the canisters drops by half, and the heat output drops proportionally. When Voyager 1 was launched in 1977, the RTGs were producing about 470 watts of electrical power. By 2024, that figure had dropped to somewhere around 285 watts, a reduction of nearly 40% over the spacecraft's operational lifetime, and it will keep dropping. The mathematics of radioactive decay are relentless and precise. There is no way to slow them, no way to add more fuel, no way to arrest the gradual dimming of the only flame keeping Voyager 1 alive. NASA's engineers have been managing this slow decline with extraordinary care over the decades. To extend the mission as long as possible, instruments have been switched off one by one as power became insufficient to run them all. The cameras were turned off years ago, various subsystems have been deactivated. The heaters that keep the propellant lines warm enough to function have been carefully managed. Each decision about which instrument to keep and which to sacrifice is made slowly and collaboratively, with awareness that each choice is permanent. There is no undo. When an instrument is turned off to save power, the data it would have gathered is simply never collected. It is a quiet, ongoing series of small losses, each one a door closing forever. The most optimistic projections suggest that Voyager 1 will be able to maintain contact with Earth, sending usable data back across the billions of kilometers until sometime in the 2030s. Some estimates are slightly more generous, pushing into the early 2040s if power management continues to be handled with exceptional skill. But the range is not enormous. Within roughly 10 to 20 years from now, Voyager 1 will fall silent. Not suddenly, not dramatically. There will be no explosion, no collision, no catastrophic failure. The signal will simply grow weaker as the power available to the transmitter decreases below the threshold needed to push a coherent signal across the interstellar distance. And then, at some point, the receivers on Earth will detect only noise where Voyager's voice used to be, and the conversation that has been ongoing for nearly 50 years will end. This is worth pausing on, because there is something genuinely affecting about it. For the last half-century, human beings have been talking to Voyager 1. The conversation is slow, necessarily so, because signals travelling at the speed of light take more than 23 hours to cover the distance between the spacecraft and Earth. A question asked today will receive its reply tomorrow, but the conversation has been continuous. Engineers and scientists at the Deep Space Network, a global array of enormous radio dishes used to communicate with spacecraft throughout the solar system and beyond, have been listening to Voyager 1 every day, monitoring its health, receiving its data, sending it commands. They know the spacecraft the way you know the sound of a familiar voice. And when that voice goes quiet, it will be the end of something genuinely irreplaceable. The Deep Space Network, it is worth knowing, is itself one of the quietly remarkable things humanity has built. Its largest dishes are 70 meters across, enormous concrete and steel ears turned toward the sky, capable of detecting signals so faint that they represent a tiny fraction of the power of a single light bulb, arriving from billions of kilometers away. The fact that we can hear Voyager 1 at all from this distance is a testament to both the sensitivity of our listening technology and the carefully engineered power of the spacecraft's transmitter. Voyager's radio signal leaves the antenna at about 23 watts, roughly the power of a dim light bulb, and by the time it reaches Earth, it has spread across such an enormous volume of space that the power received by our largest dishes is about 20 billion times smaller than what a digital watch needs to run. That we hear it at all is a kind of miracle of physics and engineering, but the silence, when it comes, will not mean the end of Voyager's journey. It will only mean the end of our ability to follow it directly. The spacecraft will continue moving exactly as it has been moving, following the same laws of physics, covering the same roughly 1.5 million kilometers per day, drifting further and further into the interstellar medium. Its silence will not change its trajectory. It will not make it less real. It will simply become, from our perspective, invisible. A blind traveler in the dark, moving away from us at 17 kilometers every second, carrying its golden message into a future we cannot see. There is a philosophical dimension to this silence that is worth considering gently. For as long as Voyager 1 has been transmitting, it has had a kind of presence in the world, an active, ongoing reality that is maintained partly by our attention. Scientists read its data, engineers monitor its systems, journalists write about its milestones. Ordinary people occasionally look up and know that somewhere out there, beyond the edge of the solar system, something we made is still alive. That awareness, however background it might be in most people's lives, is a form of connection. The spacecraft is not just a physical object drifting through space. It is also an idea, alive in the minds of the people who know about it. When Voyager 1 falls silent, that active connection breaks. The spacecraft becomes something different. It becomes a relic, a physical artifact of human history, drifting through interstellar space without any ongoing link to the civilization that created it. Like a note in a bottle, once sealed and thrown into the sea, it is no longer connected to the hand that wrote it. It belongs, in a sense, to the universe now. And the universe is not going to take particular care of it or keep track of where it is or wonder how far it has gone. It will simply drift, indifferent to its origin, subject only to the laws of physics, for as long as those laws hold. But here is something worth noting. Even after Voyager 1 goes silent, we will not entirely lose track of it. Not right away. Using the precise orbital mechanics and known physics of its trajectory, scientists will be able to calculate where it is with reasonable accuracy for quite some time after the signal dies. The mathematics of its motion are well enough understood that its position can be projected forward, even without a live signal to confirm it. The uncertainty in that projection will grow over time, as small gravitational influences from passing stars compound, and as the limits of our knowledge of the interstellar medium become more apparent. But for centuries, perhaps for millennia, the calculated position of Voyager 1 will remain meaningful. Future generations, if they choose to look, will be able to point at a patch of sky and say, somewhere in that direction, roughly that far away, there is a machine we made. It is still moving. Eventually, the uncertainty will grow large enough that the calculation loses its precision. The exact position of Voyager 1 will become a question that cannot be answered without going there to look. And going there, with any technology we can currently imagine, is not something that will happen in any near future. The distances are simply too large and our propulsion systems too slow. If we want to catch up to Voyager 1 at its current location, we would need to travel faster than it is moving, which requires a spacecraft capable of exceeding 17 kilometers per second, and we would need to aim at where it will be when we arrive, not where it is now, which requires precise projections of its trajectory. It is technically conceivable, but it is not imminent. So Voyager 1 will drift beyond our practical reach, beyond our ability to track with precision, beyond the reach of any antenna we currently have or plan to build, and it will keep drifting through the interstellar medium past the slow, invisible paths of stars that it will not come anywhere near close enough to interact with in any meaningful way. Through a darkness that has no landmarks, no destinations, no welcoming light. Just the quiet motion of a machine that was built to go, and went, and has not stopped. The power winding down in Voyager 1's RTGs is, in a way, the spacecraft's heartbeat. And like a heartbeat, it has a finite number of remaining beats. We can count them, at least approximately. We know the half-life, we know the current power output, we can draw the curve. And the curve is clearly, gently, inevitably descending towards zero. There will be a last reading from the plasma wave instrument, a last measurement of the magnetic field, a last transmission from the onboard computer, and then the spacecraft's electronic life will end, even as its physical journey continues for millions of years beyond that moment. There is something in that image, the body still moving long after the heart has stopped, that resonates in a way that is hard to articulate but easy to feel. We are used to thinking of things as alive as long as they are functioning. But Voyager 1 will continue to be real, to occupy space, to move through the universe, long after it has stopped functioning by any definition. Its silence will not diminish its reality. If anything, the silence makes it more mysterious. A thing that moves without speaking, a presence without a voice, an artifact of a civilization that may or may not still exist, carrying a message toward a destination it will never reach. The engineers who built Voyager 1 are, most of them, no longer alive or are very old now. The scientists who designed the golden record are aging. The people who cheered the launch in 1977 are grandparents or great-grandparents or gone. The civilization that built this machine has changed enormously even in the 50 years since launch. Languages have shifted, technologies have transformed, entire political structures that existed in 1977 have dissolved and reformed. And through all of it, Voyager 1 has kept moving, indifferent to the changes it left behind, focused in its mechanical, unthinking way on the single purpose it was built for, which was simply to go. In the coming thousands and millions of years, the civilization that built Voyager 1 will change beyond any recognition. Whatever humanity becomes, whatever forms our descendants take, whether biological or digital or something we have no category for yet, will bear little resemblance to the people who stood in Florida in September of 1977 and watched a rocket rise into the sky. And yet the thing they sent will still be out there, carrying the sounds they recorded and the images they selected and the mathematics they calculated, unchanged, except for the patient erosion of interstellar dust and radiation, a frozen moment of 1,977 humanity, moving silently through a universe that has aged billions of years since any of this happened. The heartbeat is slowing. In a decade or two, it will stop, and then the journey truly becomes something beyond our direct experience, something we can calculate and imagine and speak about, but can never again hear directly. The spacecraft will become, for the first time in its existence, completely and finally alone, moving through interstellar space without any connection to the world that made it. And that aloneness, that profound, unreachable separateness, is in some ways the beginning of the real story. Because what happens to Voyager 1 after the silence begins is a story told not in data but in physics, in gravity, in the slow, patient arithmetic of time. There is a structure surrounding our solar system that no human instrument has ever directly observed, and yet we are confident it exists. We have never photographed it. We have never flown through it. We have never sampled its material or measured its density or mapped its extent with any direct measurement. And yet we know it is there, because the comets that fall into the inner solar system from unexpected directions, arriving from angles that have nothing to do with the plane where the planets orbit, carry the signature of their origin in their orbital paths. The mathematics of where they come from points, unmistakably, to a vast, spherical shell of icy bodies surrounding the solar system at enormous distance. A shell so remote that it sits near the threshold between the Sun's gravitational dominance and the gravitational influence of neighbouring stars. This is the Oort cloud, and it is, in a very real sense, the outermost boundary of our home. The Oort cloud is not a wall or a sharp boundary. It is more like a vast, diffuse swarm. Billions, possibly trillions of icy objects, ranging in size from small boulders to bodies hundreds of kilometres across, scattered across an enormous spherical volume of space surrounding the Sun. These objects are so far from the Sun that they barely feel its warmth. They orbit so slowly, at such enormous distances, that a single orbit might take millions of years. They are, in every practical sense, frozen in time, relics of the early solar system, material that was scattered outward by the gravitational dynamics of the young planets and has been sitting in the cold dark ever since. The inner edge of the Oort cloud is thought to begin at roughly 2,000 astronomical units from the Sun. An astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So the inner Oort cloud begins at about 300 billion kilometers, or roughly 2,000 times the Earth-Sun distance. Voyager 1, currently about 160 astronomical units from the Sun, has a significant journey ahead of it before it even enters this region. The outer edge of the Oort cloud extends perhaps to 100,000 astronomical units, or even 200,000, placing it at a distance of about 1 to 2 light-years from the Sun. That outer edge is genuinely close to the point where the Sun's gravity and the gravity of nearby stars are roughly equally matched, a gravitational no-man's land where the tenuous loyalty of these frozen bodies could, with the right perturbation, be shifted toward either direction. At Voyager 1's current speed, it will take approximately 300 years to begin entering the inner Oort cloud, and roughly 30,000 years to pass through the entire structure and emerge on the far side. During this passage, the spacecraft will be moving through a region that is, by any comparison to the inner solar system, still essentially empty. The objects in the Oort cloud are separated from each other by enormous distances. The average spacing between Oort cloud bodies is many times larger than the distance between Earth and the Sun. The chance of Voyager 1 actually striking one of these objects, or even passing close enough to one to be meaningfully deflected, is vanishingly small. From a navigation standpoint, the Oort cloud is almost as empty as the interstellar space beyond it. But the Oort cloud matters for a different reason. It matters because it is where comets come from, and comets are carriers of some of the most chemically interesting material in the solar system. Long-period comets, the ones that arrive in the inner solar system from completely unexpected directions with no connection to the orbital plane of the planets, are thought to originate here. Something perturbs their orbits in the Oort cloud, a passing star, a gravitational ripple from the galactic disk, perhaps even the collective gravity of the dark matter halo that surrounds the Milky Way, and they begin the long fall inward, taking thousands or millions of years to reach the Sun. When they arrive, the Sun's heat vaporizes their icy surfaces, producing the spectacular tales of gas and dust that have captured human imagination since before recorded history. These comets carry with them material that has been sitting in the deep freeze of the outer solar system since the solar system formed, more than 4.5 billion years ago. Their composition provides a kind of time capsule, a chemical record of the conditions in the early solar nebula before the planets formed. Scientists study them with great interest for exactly this reason, and the Oort cloud, as the reservoir from which these comets come, represents a vast archive of primordial solar system material stored in the cold and dark for billions of years, waiting to be disturbed. As Voyager 1 moves through this region over the coming centuries and millennia, it will pass through this archive without knowing it. The spacecraft has no instruments capable of detecting the Oort cloud objects it might theoretically be near, and the density of objects is low enough that it will almost certainly pass through the entire cloud without a significant encounter. But there is something poetic about the image. A machine built by creatures who live on a small planet in the inner solar system, passing through the outermost frozen halo of that same system, the boundary region between what belongs to our star and what belongs to the galaxy. Like a traveller passing through a border region, not quite in one country or the other, in a transition zone that belongs to both and to neither. It is also in the Oort cloud region that the Sun's gravity begins to lose its decisive authority. Inside the cloud, the Sun is still clearly the dominant gravitational influence. Everything in the cloud is technically orbiting the Sun, however slowly and distantly. But at the outer edge of the cloud, the gravity of nearby stars becomes comparable. The Alpha Centauri system, the nearest stellar neighbours, exert their own gravitational pull on the objects in the outer Oort cloud. So do other nearby stars. Over geological timescales, these gravitational influences slowly reshape the outer Oort cloud, nudging objects out of stable orbits and sending some of them falling inward as comets. The Oort cloud is not a static structure. It breathes and shifts, slowly, over millions of years, shaped by the tidal forces of the galaxy and the individual gravitational influences of passing stars. This is the environment Voyager 1 will be passing through during the first phase of its long future. Not the dramatic, active environment of the inner solar system with its planets and moons and constantly churning activity, not yet the truly interstellar environment beyond the Sun's gravitational reach, but something in between, a transitional zone that is simultaneously part of our solar system and part of the wider galaxy. A place where the familiar and the alien overlap, where the icy echoes of our solar system's birth hover in the darkness alongside particles that were accelerated by supernovas on the other side of the Milky Way. One of the interesting things to consider about Voyager 1's passage through the Oort cloud is what the Sun will look like from that distance. As the spacecraft moves deeper into the cloud, the Sun will grow dimmer. From the inner edge of the Oort cloud at 2,000 astronomical units, the Sun is already far dimmer than it appears from Earth, reduced to an extraordinarily bright star rather than the blazing disk we know. From the outer edge at 100,000 astronomical units, the Sun is simply one star among many, still the brightest point of light in Voyager's vicinity, but not dramatically so. The familiar star that has been, for all of Earth's history, the source of all light and warmth and life, will have become just another star in the sky. Bright, but not dominant, one among thousands visible to an imaginary eye aboard the spacecraft. This transition, from a solar system bathed in sunlight to a cold interstellar environment where the Sun is merely another star, is one of the most evocative things to imagine about Voyager's long future. There will be a moment, a specific distance, where the Sun's light becomes no more significant than the light of the nearest 100 stars combined, a moment where our home star loses its visual dominance over the night sky. And Voyager 1, moving silently through the dark, will pass through that moment without registering it, without any sensor to detect the significance of it, and will continue on its way. Beyond the Oort cloud, Voyager 1 enters a region that is, in the most literal sense possible, not our solar system anymore. Not even the outermost, most tenuous suburb of it. At distances greater than roughly 100,000 to 200,000 astronomical units, the Sun's gravitational hold becomes comparable to or weaker than the collective gravitational field of neighbouring stars. Objects at this distance are not reliably orbiting the Sun. They are in a kind of shared gravitational custody, influenced by multiple stars simultaneously. This is where our solar system ends and where the interstellar medium, in the fullest sense of that phrase, begins. Voyager 1 has technically already crossed the heliopause, the boundary of the Sun's wind, but it has not yet escaped the Sun's gravity, and will not for tens of thousands of years. The gravitational influence of the Sun extends much further than the solar wind, because gravity falls off more slowly with distance than the particle pressure of the solar wind does. So there are two different boundaries to consider. The heliopause, which Voyager crossed in 2012 and which represents the boundary of the Sun's wind and magnetic field, and the outer gravitational boundary, sometimes called the gravitational sphere of influence, which Voyager will not cross for tens of thousands of years, and which represents the point where the Sun's gravity loses its dominance over competing gravitational influences. After that second boundary, Voyager 1 will be, in the fullest sense, interstellar, moving through space that is not dominated by any single star, shaped by the collective gravitational field of the galaxy itself, subject to the slow tidal forces of the galactic disk, and influenced by whatever stars happen to be relatively nearby at any given point in its journey. This transition will not happen at a defined moment. It will be a gradual shift, like the way dawn gives way to full morning without any precise instant when night officially ends. But it is real, and it is coming, and when it is complete, Voyager 1 will be as free as anything of human origin has ever been. The passage through the Oort cloud region, spanning thousands of years, is also a period during which Earth will be changing. Not dramatically on any human timescale, but meaningfully on geological ones. Ice ages will come and go. Coastlines will shift as sea levels fluctuate. Species will evolve and go extinct. Human civilization, if it continues, will undergo changes so profound that the people of today would likely find the world of 30,000 years hence as alien as we find the Paleolithic. And through all of that slow transformation on Earth, Voyager 1 will be crossing the outer boundary of the solar system, moving from one realm to another, one tiny step at a time, 17 kilometers every second. It is a good reminder that the universe operates on timescales that dwarf human history. The 30,000 years it will take Voyager to cross the Oort cloud contains within it approximately 6 full spans of all recorded human civilization. Entire civilizations will rise and fall during the time it takes the spacecraft to pass through the frozen outer halo of our solar system. And when it emerges on the far side, truly free of the Sun's gravitational influence, the question of where it goes next will be governed not by the Sun, but by the stars, and by the slow, patient gravity of the galaxy itself. The stars are not still. This is one of those facts that sounds simple until you really sit with it. We look at the night sky and the stars appear fixed, reliable, permanent. The constellations our great-grandparents knew are the constellations we know today. Orion looks the same as it did to the ancient Greeks. The Big Dipper holds its familiar shape. The sky has a continuity that human civilization has been able to count on for all of recorded history. And yet, underneath that apparent stillness, all of the stars are moving. Every single one of them is following its own orbit around the center of the Milky Way, moving at speeds of tens to hundreds of kilometers per second, slowly but surely shifting their positions relative to each other and relative to us. The reason we do not notice this is that the distances involved are so enormous that even fast stellar motion, measured in kilometers per second, produces only a tiny angular change as seen from Earth over the span of a human lifetime. But over thousands of years, that change adds up. Over tens of thousands of years, the night sky would look recognizably different. Over hundreds of thousands of years, the constellations would be unrecognizable. The stars that form Orion today are not physically close to each other. They just happen to lie in roughly the same direction from Earth at various distances, and the chance alignment of their positions creates the pattern we see. As the stars move along their individual orbits, that chance alignment dissolves and new different patterns emerge. For Voyager 1, this stellar motion has a very specific and calculable consequence. The spacecraft is moving through interstellar space, and the stars around it are also moving. This means that over long enough timescales, Voyager 1 will have close passes with various stars, not close in any dangerous sense, not close enough to be captured by a star's gravity, or to collide with any planetary system, but close enough that the star in question will be the nearest star to Voyager 1 for a period, and its gravitational influence will be the dominant one on the spacecraft's path. The most precisely calculated close stellar encounter in Voyager 1's near future involves a star called Gliese 445. This is a dim red dwarf star in the constellation Camelopardalis, currently about 17 light-years from Earth. Red dwarfs are the most common type of star in the Milky Way, much smaller and cooler and dimmer than our Sun, burning their hydrogen so slowly and carefully that many of them will continue to shine for trillions of years. Gliese 445 is one of these small, steady, patient suns, unremarkable in most ways but notable for one thing. Its current trajectory through the galaxy is carrying it toward our region of space. It is, relative to the Sun, approaching us. Calculations based on precise measurements of Gliese 445's position and velocity, made possible in large part by data from the Gaia Space Telescope, indicate that in approximately 40,000 years, this star will make its closest approach to our solar system, passing at a distance of roughly 3.45 light-years. That is closer than any star currently is to us, though still enormously distant in any practical sense. During this same period, Voyager 1, moving in the general direction of Ophiuchus, will pass within a comparable distance of Gliese 445, perhaps as close as 1.7 light-years. 1.7 light-years. This is the closest any star will come to Voyager 1-inch, the foreseeable future, and it is still an immense distance. To put it in perspective, the nearest star to Earth right now, Proxima Centauri, is 4.24 light-years away. Voyager 1's closest stellar encounter in the next million years will bring it within roughly 1.7 light-years of another star, which is still less than half the distance to our current nearest neighbour. So close, in the language of interstellar space, is a relative term. Even the closest stellar encounter Voyager 1 will experience is still a distance so vast that the star would appear only as an unusually bright point of light, not a disk, not something that would cast visible light on the spacecraft's surface, just a bright star, a sun, from very far away. The gravitational effect of this encounter on Voyager 1's trajectory will be measurable but not dramatic. At 1.7 light-years, Gliese 445's gravity will gently curve Voyager's path, nudging it slightly in one direction. The deflection will not be large enough to capture the spacecraft or significantly change its overall direction of travel, but it will be large enough to matter for long-term trajectory predictions. This is one of the reasons why predicting Voyager 1's exact position a million years from now requires accounting for these stellar encounters. They are small perturbations, but they accumulate. There are other predicted encounters as well. The study of stellar close approaches to our solar system has become a rich area of research since the Gaia satellite began providing precise stellar positions and velocities. Scientists have identified dozens of stars that will pass within a few light-years of our solar system over the next few million years, any of which could also represent a close approach to Voyager 1, depending on where in interstellar space the spacecraft happens to be at the relevant time. A star called HIP 85605 was briefly thought to be a very close future passer, but more precise measurements revised its trajectory to a less alarming distance. The research continues, and the catalogue of predicted close stellar encounters grows more refined with each new Gaia data release. What these encounters collectively tell us is something important about the nature of the interstellar environment Voyager 1 is moving through. It is not static. It is not empty, in the sense of being unchanging. Stars are moving through it on their individual orbital paths, and over millions of years, the local stellar neighbourhood shifts substantially. Stars that are far away today will be relatively close in 100,000 years. Stars that are currently nearby will be far away by then. The space around Voyager 1 will change, slowly and continuously, as its surrounding stellar population evolves. For Voyager 1 itself, these gravitational nudges from passing stars represent the primary mechanism by which its trajectory will deviate from a simple straight-line path over millions of years. Without any active propulsion and with the only significant forces being gravity, the spacecraft's path through interstellar space is essentially a geodesic, the curved path defined by the gravitational field of every massive object in the galaxy. Over short timescales, this looks like a straight line. Over millions of years, the accumulated gravitational influences of dozens of stellar encounters will bend it, gently and cumulatively, into something more complex. This raises a question that is worth sitting with. Is there any possibility, however remote, that one of these stellar encounters could result in Voyager 1 being captured by a star's gravity, becoming, in some distant future, an object orbiting a star that is not our Sun? The answer is almost certainly no, at least on any timescale we can meaningfully consider. The speeds involved make capture essentially impossible without a very specific and very unlikely set of circumstances. For a spacecraft moving at 17 kilometers per second relative to a star it is approaching, the gravitational pull of a normal star at a distance of even 1 light-year is far too weak to slow the spacecraft enough to capture it. The mathematics of the energy involved make this clear. To be captured by a star's gravity, you generally need to lose enough energy to fall below escape velocity, which typically requires an interaction with multiple objects in a carefully choreographed gravitational dance. With just a single star and a spacecraft moving at interstellar speeds, capture is essentially off the table. So Voyager 1 will not become someone else's planet. It will not be drawn into orbit around Gliese 445 or any other star it passes near. It will continue its drift, nudged slightly by each encounter, but essentially free, carrying its path forward through an interstellar medium that grows slightly different in character as the spacecraft moves further from the Sun. There is something quietly beautiful about the stellar encounters in Voyager 1's future. The idea that this small machine, built by beings on a small planet, will in 40,000 years be closer to a different sun than any star currently is to ours. That it will experience, in a gravitational sense, a different star's neighborhood. That it will be, for a period, somewhat more belonging to Gliese 445's region of space than to our own. This is not dramatic in any physical sense. The spacecraft will feel nothing. Its golden record will hear nothing. But the mathematics of it is real, and there is a kind of poetry in a journey that carries something of ours through the gravitational embrace of stars we will never visit. The stars Voyager 1 will pass near over the next million years are not randomly distributed. The stellar neighborhood of the Milky Way has a particular structure, and Voyager 1's path through it is shaped by the direction it was sent and the overall motion of the Sun through the galaxy. As the spacecraft moves above the plane of the galactic disk, it enters a region where stellar density is somewhat lower than in the disk itself. The separations between nearby stars are slightly larger. The encounters, while still occurring, are somewhat less frequent. This means the trajectory is less perturbed than it might be if Voyager were heading through the denser regions of the disk. But the disk's gravity is still present. The collective mass of all the stars, gas, and dark matter in the galactic disk exerts a tidal force on everything above and below it, a gentle but real pull that tends to draw objects back toward the plane over time. This galactic tidal force is the same mechanism that is thought to perturb the outer Oort cloud objects, sending some of them falling inward as comets. For Voyager 1, this force will gradually influence its trajectory over millions of years, bending its path slightly back toward the galactic plane in a slow, smooth arc. The effect is small and cumulative, not dramatic, but over a million years it is not negligible. The galactic tide, the stellar encounters, the slow drift through the interstellar medium, these are the forces that will shape Voyager 1's path over the timescales we are considering. None of them are likely to produce a dramatic change in direction. None of them will result in the spacecraft being captured or destroyed. They will simply bend, gently and continuously, the path of a small machine moving through a galaxy that is itself moving, rotating, living its own vast life on timescales that make even a million years seem brief. And all the while, the stars that Voyager 1 passes near will themselves be changing. Red dwarfs like Gliese 445 will shine steadily for trillions of years, essentially unchanged on the timescale of a million years. Other stars that Voyager might pass near could be more variable, pulsing or flaring in ways that would briefly increase the radiation environment near the spacecraft. None of these are likely to have any significant effect on Voyager 1 itself. The spacecraft's passive structure, its metals and plastics, and the gold-plated copper of the golden record will simply continue their slow drift through whatever radiation environment they happen to be in, absorbing and deflecting whatever comes their way, accumulating the slow damage of cosmic time without any dramatic incident. In a million years, Voyager 1 will have passed through the gravitational neighborhoods of several stars. It will have been nudged gently by each of them. It will have drifted, slowly, through the interstellar medium between them, and it will still be moving, somewhere between 40 and 60 light-years from where it started, in a direction that is generally consistent with where it is heading today. The stellar encounters are not destinations, They are incidental passages, gravitational conversations between a human artifact and the stars of the Milky Way, conducted silently across distances that humble any attempt at description. Imagine standing on the surface of Earth tonight. Look up at the sky, clear and dark, find the familiar shapes. The Belt of Orion, 3 stars in a nearly perfect line. The Big Dipper, that reliable ladle hanging in the northern sky. Cassiopeia, the W shape that never quite sets for observers in the mid-northern latitudes. These patterns have been companions to human beings for as long as there have been human beings. Hunters used them for navigation, sailors used them to cross oceans, farmers used them to mark the changing seasons. The constellations are so deeply embedded in human culture, appearing in mythology and poetry and navigation manuals and children's books, that it is easy to feel they are permanent, fixed, part of the furniture of the universe. They are not. Not on the timescales we are discussing. The stars that form the constellations are not physically related to each other. They are not a cluster of stars that form together or share any common fate. They are stars scattered at various distances from Earth, some close and some far, that happen to appear in the same general direction when viewed from our particular location in the Milky Way. The alignment is a coincidence of perspective, and it is temporary. As the Sun and all the stars near it continue on their individual orbits around the galactic center, the chance alignments that create the constellations will slowly dissolve and reform into entirely different patterns. Astronomers have actually calculated what the night sky will look like at various points in the future, using the known positions and velocities of nearby stars. The changes are small over a single human lifetime, barely noticeable from generation to generation. But over 50,000 years, the sky begins to look significantly different. Over 100,000 years, the familiar constellations are distorted beyond easy recognition. And over 1,000,000 years, the sky from Earth would look entirely unlike the sky we know, a completely different arrangement of stars, shaped by the slow drift of our stellar neighborhood through the galaxy. From Voyager 1's perspective, the changes in the sky would be even more dramatic, because the spacecraft is not only drifting through time but also through space, moving away from Earth at a significant fraction of a light-year per century. As it moves, the apparent positions of stars shift not just because of stellar proper motion, the real movement of each star through space, but also because of the changing perspective created by Voyager's own motion. This combination of parallax, the perspective shift caused by moving to a new viewpoint, and proper motion, the real stellar drift, means that the sky as seen from Voyager 1 will change steadily and significantly over thousands of years. In the first few centuries after Voyager 1 falls silent, the changes in the sky from its perspective would be subtle. Stars would drift slightly from their familiar positions, the nearest ones moving most, the distant ones barely at all. The Sun, growing ever dimmer as Voyager moves further away, would still be recognizable as the brightest or one of the brightest stars in the sky for a while. At a distance of 1 light-year, roughly 63,000 astronomical units, the Sun would shine at about the brightness of Sirius does from Earth. Still one of the most prominent stars in the sky, but no longer overwhelmingly dominant. As Voyager moves further, the Sun will continue to dim. At 5 light-years, the distance of Alpha Centauri from Earth, the Sun would be a bright but unremarkable star, one of the top 10 brightest in the sky, but not dramatically different from its neighbours. At 10 light-years, it would have faded to a more modest brightness, still easily visible to the naked eye of any imagined observer, but no longer among the handful of truly prominent stars. At 50 light-years, the Sun would be a dim star, barely visible to the naked eye under the best conditions, indistinguishable from the background of thousands of other dim stars without knowing precisely where to look. This dimming of the Sun from Voyager 1's perspective is one of the most evocative aspects of the spacecraft's long journey. There will be a point, somewhere around 50 to 100 light-years from Earth, when the Sun becomes invisible to the naked eye from Voyager's location. Not because the Sun has stopped shining, it will be shining exactly as it always has, pouring out the same steady energy it has produced for the last 5 billion years. But the distance will have become so great that the Sun's light, spread across an enormous sphere of space surrounding it, will have diluted to the point of invisibility at Voyager's position. When that happens, Voyager 1 will be in a piece of sky where the Sun cannot be seen without a telescope. It will have travelled beyond the range where our home star is directly visible. It will be, in a literal optical sense, beyond the reach of the Sun's naked eye influence, and it will keep going. The star that will become increasingly prominent in Voyager's sky as the Sun fades is harder to specify. because it depends on which stars happen to be nearby at any given point in the spacecraft's journey, and that changes as both Voyager and the stars around it move. But there will always be nearby stars, and those nearby stars will look bright. From Voyager's perspective, 50 light-years from Earth, the sky will contain a set of prominent stars that is partially familiar and partially completely different from what we see from Earth today. Some of the bright stars we know, the ones that are intrinsically very luminous and visible from Earth despite being very far away, will still be visible from Voyager because their intrinsic brightness more than compensates for the increased distance. But the stars that are currently prominent in our sky because they are close to us, not because they are intrinsically bright, will have changed. New close stars, ones that happen to be near Voyager 1's position in interstellar space, will dominate the local sky. There is something philosophically rich about this. The night sky is not a universal backdrop. It is a local view, shaped entirely by your position in space. Every inhabited world in the galaxy, if there are any, sees a different sky. The patterns they draw in the stars, the stories they tell about them, the navigation systems they build around them, are all shaped by where they happen to be. The sky is personal in that sense. Our constellations are ours, not because they have any cosmic significance, but because they are what you see from here. Voyager 1's sky will become something that no one in our civilization has ever seen. A view from a vantage point that has never been occupied by any human instrument until now. The set of stars visible from Voyager's position 50 light-years away is not a sky that any ancient astronomer or modern scientist has ever observed. It is new, genuinely new, in the sense that no instrument of human observation has ever been positioned to see it. Of course, Voyager 1 has no cameras. The cameras were turned off decades ago. The spacecraft cannot see. It cannot observe the new sky around it. It can only drift through it, silent and sightless, its scientific instruments long since powered down, its golden record sealed in its protective cover, unable to appreciate the view. There is something melancholy about this if you let yourself feel it. We sent something to the one place in the universe that would have the most remarkable and unprecedented view of the sky, and we removed its eyes before it got there. But perhaps this is the right way to think about it. Voyager 1 is not a tourist. It is not a sightseer. It is a messenger. Its purpose was never to appreciate the view, but to carry something into the universe, to extend the reach of human presence into a space that had never been touched by anything we made. The view is not for Voyager 1. It is in a sense for us. We know the view is there. We can calculate it, model it, imagine it. And the fact that Voyager 1 is there, occupying that vantage point even without seeing it, is enough. The presence is what matters. The reaching is what matters. The changing sky also raises a broader question about what it means for a human artifact to drift through a universe that is itself changing. The Milky Way galaxy is not the same today as it was 1,000,000 years ago, and it will not be the same 1,000,000 years from now. The spiral arms are not fixed structures. They are density waves, patterns of compression in the galactic disk that stars move in and out of over time. Stars form in the arms, are born in the dense gas clouds there, and then drift through and out of the arms on their individual orbits. The galaxy as a whole is rotating, but different parts rotate at different speeds, and the spiral structure is a slow, continuously evolving pattern. 1,000,000 years from now, the Milky Way's spiral structure will look slightly different from what it does today. Our Sun, which is currently between two spiral arms, will have moved along its orbit by roughly 220 km per second times 3x10, 13 seconds, which is roughly a full percent of the way around the galaxy. Voyager 1, moving at its much slower speed relative to the stars, will be in a slightly different position relative to the galactic structure. Though the overall context of the Orion arm of the Milky Way will be broadly similar, the galaxy does not change fast enough, on a 1,000,000-year timescale, to make the context fundamentally unrecognizable, but it changes enough that careful measurements would show the difference. The sky that Voyager 1 is drifting through is not, in a cosmic sense, a fixed place. It is a snapshot of a dynamic, evolving system, seen from a particular moment in the galaxy's long history. In 1,000,000,000 years, the sky from anywhere near our current location in the Milky Way will look dramatically different, because the Andromeda Galaxy will by then be in the early stages of its collision and merger with the Milky Way. That merger, which has been predicted for decades based on measurements of Andromeda's approach velocity, will scramble the orderly structure of both galaxies, eventually producing a large elliptical galaxy that bears little resemblance to either of its progenitors. But that is far beyond the million-year timescale we are focusing on. In a million years, the galaxy looks almost, though not quite, the same as today. The changing sky is ultimately a story about perspective. Where you are in space determines what you see. How long you have been there determines how much has changed. Voyager 1, moving through an evolving galaxy, seeing a changing sky it cannot see, carrying a record of a world that is itself changing, is an artifact that sits at the intersection of multiple forms of change simultaneously. The spacecraft is stationary in the sense that it cannot act, cannot respond, cannot adapt, but it is embedded in a universe that is never stationary, and the contrast between the stillness of the machine and the vast, slow movement of everything around it is one of the most striking aspects of its long future. In 100,000 years, someone standing on Earth, if anyone still is, and looking at the sky, will see a constellation where Voyager 1 is located. They will not know probably that there is a machine out there, but if they did know, and if they could look in the right direction with the right instrument, they would see the Sun, a faint, small star, roughly 9 light-years away by then, unremarkable among its neighbours, glowing steadily in a corner of a sky that bears almost no resemblance to the sky we know. The familiar and the strange will have traded places completely by then. The sky we know will be gone, and the sky that Voyager 1 drifts through will be, in the eyes of anyone then living on Earth, just as unfamiliar as Voyager's current sky is to anyone who has never left the inner solar system. While Voyager 1 drifts silently through interstellar space, the world it left behind will not stand still. Earth is not a static object any more than the galaxy is. It is a dynamic, changing, living system, driven by tectonic forces from below and atmospheric processes from above, shaped by the slow pulse of ice ages, by the gradual brightening of the sun, by the continuous evolution of life, and by all of the unpredictable choices and consequences of any civilizations that might exist on its surface. 1 million years of Earth history is not a stable plateau. It is a journey of its own, one that will produce a world recognizable in its basic outlines, but transformed in almost every detail. The most immediate and human scale of change is, of course, human civilization itself. 1 million years ago, our ancestors were using simple stone tools and living in small nomadic groups. In the million years since, we developed language, agriculture, cities, science, global communication, space travel. The pace of change has been accelerating, particularly in the last few centuries. If the rate of change continues anywhere near its current trajectory, 1 million years of human history from now will produce something that bears no recognizable relationship to what we are today. The beings, or entities, or whatever descendants of humanity might exist 1 million years from now, will look back at 2024 the way we look back at the creatures making stone tools on the African savanna, with curiosity, perhaps with affection, but with an enormous gulf of change separating them from that origin. But there are reasons to be cautious about assuming that 1 million years of linear progress will simply produce a more technologically advanced version of what we are today. Civilizations are fragile. They rise and fall. The history of the last 10,000 years includes the rise and fall of dozens of complex civilizations, some of which left no successors and were forgotten for millennia. The future is not guaranteed to be smooth. Ice ages will return. Supervolcanic eruptions will periodically alter the climate. Asteroid impacts, while rare, are statistically inevitable over long enough timescales. Pandemics and ecological shifts will continue to challenge any biological civilization, and the choices that human beings or their descendants make, individually and collectively, will shape outcomes in ways that are genuinely impossible to predict. What we can say with reasonable confidence is that the biological diversity of Earth will change substantially over 1 million years. Evolution does not stop. Populations isolated by geography or climate will diverge, new species will emerge, existing species will go extinct. The mammals, birds, reptiles, fish and insects alive today are not the same as those that lived 1 million years ago, and the species alive in 1 million years will not be the same as those alive today. This is not a speculation. It is a direct prediction from evolutionary biology, as certain as the prediction that the sun will rise tomorrow. Life on Earth will be different in 1 million years, probably in many ways we cannot specifically anticipate. The geological changes will also be real and significant. The tectonic plates that carry the continents will have moved. The The rate of plate tectonic motion is roughly a few centimeters per year, which over 1 million years adds up to tens of kilometers of drift. The Atlantic Ocean will be slightly wider. The Himalayas will be slightly higher, or slightly eroded, depending on which forces dominate. The ongoing collision between the Indian subcontinent and the Eurasian plate will have continued, perhaps creating new mountain ranges or reshaping existing ones. California, which sits on the boundary between the Pacific and North American tectonic plates, will have moved significantly northward relative to the rest of North America, though whether by centimeters or by larger amounts depends on ongoing geological processes. The coastlines of every continent will be different, partly from tectonic motion and partly from changes in sea level driven by climate cycles. Speaking of climate, 1 million years is enough time to include multiple complete ice age cycles. The pattern of ice ages is driven primarily by the Milankovitch cycles, the slow, regular variations in Earth's orbit and axial tilt caused by gravitational interactions with Jupiter, Saturn, and the other planets. These variations change how much sunlight reaches different parts of Earth at different times of year, triggering the advance and retreat of ice sheets over timescales of tens of thousands of years. In 1 million years, there will be roughly 10 to 20 complete cycles of glacial advance and retreat, each one profoundly reshaping the landscape, the sea level, the climate, and the distribution of life. Northern Europe and North America will be buried under ice sheets kilometers thick for significant portions of the coming 1 million years. The Sahara will green and brown cyclically, as it has done repeatedly in the past. Species will shift their ranges poleward and equatorward, following the climate, evolving as they go. The Sun itself will be slightly different in 1 million years. The Sun is a stable middle-aged star, and its luminosity is increasing very gradually as it fuses hydrogen into helium in its core, and the core contracts and heats slightly over time. The rate of this brightening is roughly 1% per 100 million years. Over 1 million years, the effect is very small, less than 1/100% increase in solar output. Earth's average temperature would be essentially unchanged by this tiny brightening on a 1 million-year timescale, but over hundreds of millions of years, the cumulative brightening will become significant enough to matter deeply for Earth's climate and habitability. The Sun of 1 million years from now is, for practical purposes, the same Sun as today. The Moon will also have moved slightly. The Moon is gradually receding from Earth, pushed outward by tidal interactions at a rate of about 3.8 centimeters per year. Over 1 million years, this adds up to 38 kilometers of additional distance. The Moon is currently about 384,000 kilometers away, so this is a very small fractional change, less than 0.01%. The effects on Earth's tides and on the stabilization of Earth's axial tilt, which the Moon helps regulate, will be essentially negligible on this timescale. The Moon, like the Sun, will look and behave for all practical purposes the same in 1 million years as it does today. What about the possibility that humanity or its descendants might, in 1 million years, have developed technologies capable of interstellar travel? This is where the future becomes genuinely speculative, but it is worth considering because it has a direct bearing on the question of whether Voyager 1 might eventually be found or retrieved. 1 million years is an enormous amount of time for technological development. We went from stone tools to spacecraft in 300,000 years. In 1 million years, what might be possible? Science fiction has offered countless visions of faster-than-light travel, of colony ships crossing the galaxy, of civilizations spread across multiple star systems. Whether any of these visions will be realized depends on physics we do not fully understand, and engineering challenges we cannot yet assess. What we can say is that if any descendant of humanity, biological or artificial, achieves true interstellar travel within the next 1 million years, Voyager 1 would be, in principle, recoverable. The spacecraft will still exist. It will still be physically intact, or close to it. Its golden record will still be readable. Knowing the spacecraft's approximate trajectory, a future civilization with interstellar capability could, in principle, mount an expedition to retrieve it. The idea of bringing Voyager 1 home, of placing it in a museum where some future version of humanity could look at it and understand where they came from, is not physically impossible. It is just technologically far beyond anything we can currently do. Alternatively, if any other intelligent civilization in the galaxy has developed interstellar travel, and if Voyager 1 happens to drift close enough to one of their inhabited systems, they would have the possibility of detecting and retrieving the spacecraft. This is, as far as we can calculate, extraordinarily unlikely. The galaxy is large and Voyager is small, and its path through interstellar space will not bring it particularly close to any known stellar system for the foreseeable future. But it is not impossible in principle. This is, in essence, the hope behind the golden record. Not a confident expectation, but an acknowledgement of the possibility. One thing that will not change over 1,000,000 years is the basic structure of physics. The laws that govern gravity and electromagnetism and quantum mechanics are not expected to change on any timescale relevant to this discussion. The universe 1,000,000 years from now will operate by the same rules as today. Stars will shine by nuclear fusion. Gravity will curve trajectories. Light will travel at the same speed. The constants of nature are, as far as we know, genuinely constant. This means that Voyager 1's behavior, its speed, its trajectory, its structural integrity, can be predicted using the same physics we use today. The spacecraft's future is, in this sense, more predictable than Earth's, because the laws it operates under are simpler and more stable than the complex, chaotic, life-filled dynamics of a living planet. There is something grounding in that comparison. Earth is uncertain, complex, full of contingency and unpredictability. Voyager 1 is simple, governed by laws that do not change, moving on a path that can be calculated. In one sense, the spacecraft has a more knowable future than the planet that made it, and in another sense, the planet, with all its uncertainty and complexity and life, is vastly richer than the silent machine drifting away from it. This contrast between the mechanical predictability of the spacecraft and the living unpredictability of the world is part of what makes Voyager 1's story so resonant. It is the intersection of two very different kinds of futures, meeting at the moment of launch and then diverging. One into the simple physics of interstellar space, and one into the messy, beautiful, unpredictable turbulence of a living world. Earth, whatever it becomes in 1,000,000 years, will still be there, orbiting the sun, being warmed by its light, hosting whatever forms of life have evolved by then. The continents will be slightly rearranged. The climate will be different. The sky will look different, both because of changes in Earth's atmosphere and because the stars themselves will have shifted. But the planet will be fundamentally the place it is today, a rocky world with an iron core and a thin atmosphere and liquid water on its surface, orbiting an ordinary star in the outer reaches of the Milky Way. And somewhere in that changed future sky, if anyone on that future Earth knows where to look and has the instruments to see, there will be a faint, moving point of light, too dim to see without a powerful telescope, but detectable in principle, moving through the interstellar medium at 17 kilometers per second, carrying a golden record. Carrying sounds of a world that by then will be 1,000,000 years in its own past, drifting quietly through the dark. There is a photograph on the golden record. It is an image of a human silhouette, a woman and a man, and behind them the outline of the Voyager spacecraft itself, drawn to scale so that whoever finds the record can understand the relative size of the creatures who made it. There are images of human anatomy, of cells and organs, and the DNA double helix, the molecular blueprint of life on Earth. There are images of the solar system, of Earth from space, of landscapes and cityscapes and people eating and people laughing and people in many different cultural contexts. There is an image of a nursing mother, an image of a sunset, an image of traffic on a freeway at night, and 116 images in total, a small, carefully chosen mosaic of what it meant to be human on Earth in the year 1977, encoded in analog format on a copper disc plated with gold. The people who chose what to put on the golden record had an impossible task. They were asked to represent all of humanity and all of Earth to an audience they could not describe, in a format they could not be certain would be decoded, for a message that might never be received. Carl Sagan led the effort, and the team he assembled spent months wrestling with the question of what to include. Every choice was a statement. Every omission was a statement. If you include music from one culture and not another, you have said something. If you include images of one kind of life and not another, you have said something. The record could not contain everything, and so it had to contain something, and choosing what that something was required an act of imagination about who, or what, might eventually hear it. The music chosen for the record spans geography and history, with a deliberateness that is moving when you think about it carefully. There is a Javanese gamelan piece, the ringing, layered sound of bronze percussion instruments played in a tradition thousands of years old. There is a Navajo night chant, a ceremonial song from a culture that has existed on the North American continent for centuries. There is a Senegalese percussion piece, a Georgian choral song, a Peruvian wedding song, panpipes from the Solomon Islands, and alongside these there is Bach. The well-tempered clavier, the first movement of a Brandenburg concerto, a Beethoven string quartet, a Mozart aria, Louis Armstrong playing melancholy blues, Chuck Berry playing Johnny B, Good, a Blind Willie Johnson blues, Valia Balkanska singing a Bulgarian folk song. The variety is intentional. The people who assembled the record did not want to represent a single musical tradition as if it were the only one on Earth. They wanted to gesture at the breadth of human musical expression, the remarkable fact that this species, on this planet, has independently invented music in virtually every culture, in every period of history, and has produced a diversity of musical forms that no single listening session could encompass. Music is one of the things that makes us human in a deep sense, not because other animals do not communicate in sonic ways, but because the complexity, the emotional range, the sheer variety of what human music does and means and says is something we have no evidence of in any other species we know of. The Golden Record's music is an argument, implicitly, for the richness of what exists on Earth. The greetings on the record are even more moving, in a quieter way. 55 human languages, speaking brief messages of welcome and peace. Some of the languages are major world languages, still spoken by hundreds of millions of people today. Some are smaller languages, spoken by a few thousand people. Some, by now, may be endangered or extinct. The voices are from 1977, recorded in the months before the launch, spoken by people who are now elderly or gone. Their voices are preserved on a gold-plated disc, moving through interstellar space at 17 kilometers per second, carrying the sounds of languages that will, in a million years, have evolved beyond recognition on Earth or perhaps vanished entirely. There is a greeting in Sumerian, one of the oldest known written languages, already ancient by the time of Julius Caesar. There is one in Hindi, in Mandarin, in English. There is one in Welsh. There is one in a Nigerian language called Igbo. Each greeting is brief, usually just a sentence or two, saying in its particular language something like, "We send you greetings from the world of Earth. We hope that one day, in peace and friendship, we will meet." The simplicity of the messages is not a limitation. It is wisdom. There is no way to transmit the complexity of any single culture in a brief greeting, let alone the complexity of all human culture. The best you can do is gesture at the intention behind the communication. And that intention, in these greetings, is clear. We are here. We are aware. We are reaching out. The sounds of Earth on the record are, in some ways, the most affecting of all, not because they are the most complex or the most scientifically interesting, but because they are the most viscerally familiar. The sound of rain, of ocean waves, of wind, the call of a cricket, the song of a bird, the howl of a wolf, the sound of a human heartbeat, a mother cooing to a baby, the sound of footsteps on grass, a fire crackling. These are the sounds that any human being who has ever lived on Earth would recognize instantly. They are the sounds of home, recorded and sealed and sent away from home into a universe that has never heard them. The selection of these sounds was not random. It was intended to convey something about what Earth is, in a sensory way, before any attempt at language or culture or science. The committee reasoned that an intelligence advanced enough to intercept and decode the record might not share any of our assumptions about music or language or mathematics. But if they have ears or some sensory analog to ears, the sounds of waves and rain and wind might communicate something even without decoding. The naturalness of natural sounds might serve as a kind of introduction, a way of saying, this is an environment, this is a world, these are the sounds it makes when it is simply being itself. The question of who might find the golden record is one that the scientists who created it thought about carefully and, to their credit, honestly. The honest answer is that the probability of the record being found by another intelligence is extremely low by any reasonable calculation. Voyager 1 is tiny. Interstellar space is vast. The spacecraft will not pass particularly close to any star system for tens of thousands of years, and even then, its closest approach will be measured in light years, not the kind of distance where detection and retrieval would be straightforward. For an alien civilization to find Voyager 1, they would need to be scanning interstellar space with instruments sensitive enough to detect a small metallic object at distances of multiple light years, and would then need to be motivated to retrieve it. The combination of all these requirements makes the probability genuinely tiny, but the scientists sent it anyway, and they sent it not because they were naive about the probabilities, but because they understood something about what it means to communicate. Communication is not only about whether the message is received, it is also about the act of sending. The golden record is a message to the universe, but it is also a message to ourselves. It says something about what we value, about what we find beautiful, about what we think deserves to be remembered. It is an act of self-definition, performed in the knowledge that the audience may never exist, but feeling nonetheless that the act itself matters. This is an instinct as old as humanity. Cave paintings are messages to the future, painted on walls where no one was guaranteed to find them. Letters sealed in time capsules are messages to descendants who may or may not open them. Monuments built to outlast their builders are messages to time itself. The golden record is part of this ancient human impulse to make a mark, to say I was here, to reach toward a future or a universe that cannot promise to receive the message but that feels, somehow, worth addressing anyway. In 1,000,000 years, if the golden record still exists, it will be one of the oldest surviving human artifacts in the universe, assuming it has not been retrieved or destroyed in the interim. The cave paintings at Lascaux in France, some of the oldest we know of, are about 17,000 years old. The oldest stone tools are around 3.3 million years old, but they are not artifacts of civilization in the sense of intentional communication. The golden record, drifting through interstellar space for 1,000,000 years, would be a human artifact of a kind that has no precedent. Something made with intentional cultural content, preserved through the physics of its environment rather than the care of any civilization, drifting further from its origin with every passing day. The copper disc itself, plated in gold to resist corrosion, is expected to survive essentially intact for up to 1 billion years in the interstellar environment. The gold plating prevents the copper from oxidizing, and in the near vacuum of interstellar space, there is very little else to attack the material. Cosmic radiation will slowly discolor the surface. Interstellar dust impacts will gradually pit it, but the record grooves themselves, analog impressions encoding the audio information, will remain readable. The images, encoded in analog format on the record surface, will remain decodable. The mathematics inscribed on the cover, providing the key to playing the record and to locating its origin, will remain interpretable. The golden record, in 1,000,000 years, will still contain everything it contains today. This is an extraordinary thing to sit with. 1,000,000 years from now, on a small disk of copper and gold, drifting somewhere in the general direction of Ophiuchus, 50 or 60 light years from Earth, there will still be the sound of Louis Armstrong playing Melancholy Blues. There will still be the voice of a human child saying something in Sumerian. There will still be the sound of rain on a forest. There will still be the sound of a heartbeat. All of it perfectly preserved, waiting in the dark for someone or something that may never come. And perhaps that is fine. Perhaps the waiting itself, the existence of the thing that was made and sent and is still travelling, is enough. Perhaps the meaning of the golden record is not in its eventual discovery. Perhaps it is in what it reveals about the civilization that made it, that we were, for all our limitations and conflicts and uncertainties, a species that looked outward, that felt the need to speak into the dark, that believed the universe was worth addressing. The golden record will outlast every human institution. It will outlast every language on it, in their current forms. It will outlast, almost certainly, every individual human alive when it was launched. It carries the voices of people who are now gone, speaking languages that have changed, from a world that has transformed around them, and it moves, steadily and silently, through a universe that has existed for 13.8 billion years, and will exist for far longer than that, carrying this small, fragile, beautiful attempt at connection between one tiny world and everything else. There are very few things in human history that are this simultaneously humble and this ambitious. The golden record knows it may not be found. It goes anyway. It knows it may not be understood. It speaks anyway. It knows it represents only a fragment of the civilization that made it. It chooses its fragments as carefully as it can, and then it lets go and trusts the universe to do with it what it will. That, in its way, is an act of faith. Not faith in any particular religion or cosmology, but faith in the idea that reaching matters, that communication, even into an uncertain void, is meaningful, that the impulse to say something, anything, into the dark is one of the things worth preserving about us. The golden record is not the best thing humanity has ever made, but it might be the most honest. There is a particular kind of thought experiment that physicists and philosophers sometimes play with, which asks what it would mean to truly preserve a memory. Not in the sense of keeping a record, a photograph, or a written document, but in the deeper sense of keeping something genuinely alive over time. The challenge is that everything changes. Materials degrade. Languages evolve until they are unrecognizable. Institutions dissolve. Even the rocks that carry ancient writing are eventually worn away by erosion or buried by geological processes. Nothing that human beings have made has lasted for 1,000,000 years in a form that carries its original meaning intact. The oldest human artifacts, the stone tools of our distant ancestors, carry no readable intentional information. They can tell us someone was there and had hands and made choices, but not who they were or what they were thinking or what they loved. Voyager 1 changes this. For the first time in the history of our species, we have placed an intentional cultural message in an environment where it has a genuine chance of surviving for geological timescales. Not because we are better engineers than our ancestors, though we are. Not because we understand preservation better, though we do, but because we have placed the message in an environment that is, by its very nature, enormously more stable than anything on Earth. The interstellar medium is cold. It is chemically inert for all practical purposes. It contains almost no material to interact with, and it is free from the geological processes, the weather, the biological activity, the human activity that degrade everything on Earth over time. It is, paradoxically, the emptiness of interstellar space that makes it the safest archive humanity has ever used. The golden record, sealed in its protective cover, drifting through interstellar space, is expected to remain readable for roughly 1 billion years. 1 billion years. Earth is 4.5 billion years old. If the earliest single-celled life that appeared on Earth had somehow managed to place a golden record in interstellar space at the moment of its emergence, and if Voyager 1 is any guide, that record would still be readable today. We have no evidence that life on Earth has ever done anything like this before the 20th century. But the point is that the timescale is almost incomprehensible in its depth. 1 billion years of preservation, 1 billion years of waiting, in the dark for someone to come along and listen. This raises a deep question about what it means to have a legacy. In ordinary human terms, a legacy is something that outlasts a person. The children they raised, the work they produced, the influence they had on others. Most legacies are social, maintained by the attention and care of subsequent generations. The legacy of a great painter endures because people keep looking at the paintings and talking about them. The legacy of a scientist endures because people keep building on the work. These kinds of legacies are fragile, dependent on chains of human attention that can break at any point. Languages die, institutions collapse, libraries burn. The chain of attention that keeps a legacy alive can be severed by any number of causes, and once it is severed, the legacy fades into the silence of the forgotten. Voyager 1's legacy is different in kind. It does not depend on a chain of human attention. It does not require anyone on Earth to remember it, teach it, preserve it, or care about it. The physical object, moving through interstellar space, is self-sufficient as an archive. It carries its own message, in a form that does not require upkeep. It will be there whether or not anyone thinks about it, whether or not a future civilization knows it exists, whether or not any civilization exists at all. The preservation is physical, not social. It is maintained by the laws of physics rather than by the choices of people. This is genuinely new in human experience. Everything else we have tried to preserve requires maintenance, care, attention, cultural continuity. Voyager 1 requires none of these. It will drift. It will carry its message, and it will continue to do so regardless of what happens on Earth, or in the Milky Way, or in the observable universe. Not forever, not truly, because eventually even gold-plated copper is subject to the slow erosion of cosmic radiation and the very long-term instability of matter itself. But for timescales so large they have no meaning in terms of human civilization, Voyager 1 is effectively permanent. There is something both comforting and unsettling about this. Comforting, because it suggests that something real and genuine from this moment in human history will persist long past any reasonable expectation. Unsettling, because the persistence of the object is so disconnected from any continuing human awareness of it. In a million years, if no one on Earth or anywhere else knows about Voyager 1, the spacecraft will still be there, carrying its golden record, drifting through the dark. Its existence will be real and its message will be intact. But who is it for? If no one knows about it, if no one is looking for it, if no civilization is within reach of it, is its existence meaningful in any way? This is a version of the old philosophical puzzle about whether a tree falling in the forest makes a sound if no one is there to hear it. In physics, the answer is yes. The sound waves exist regardless of whether anyone perceives them. In human meaning, the answer is more complex. Meaning requires someone to do the meaning. A message with no reader is not obviously meaningful in the full human sense of the word. And yet the people who created the golden record did not feel this way. They felt that the act of creating and sending the message was meaningful in itself, regardless of whether it was received. They were making a statement about what kind of beings we are, and statements can have meaning even when the audience is hypothetical. There is a concept in philosophy called intrinsic value. The idea that some things are valuable in themselves, not because of their consequences or their usefulness to someone, but simply because of what they are. A beautiful landscape has intrinsic value, many philosophers argue, regardless of whether anyone is there to appreciate it. A piece of music has intrinsic value regardless of whether it is ever heard. By this view, the golden record has intrinsic value as a message, as an act of reaching, as a monument to a particular moment of human aspiration, regardless of whether it is ever found or decoded. Whether you find this view convincing depends on your deepest assumptions about the nature of value and meaning. But there is one thing that is not philosophically ambiguous. The fact of Voyager 1 has already had meaning. It has already changed how people think about themselves, about Earth, about the universe, about what it means to be human. The pale blue dot photograph, taken by Voyager 1-inch 1990, has profoundly affected the way many people understand their place in the cosmos. Carl Sagan's reflections on that photograph have been read by millions of people and have shifted, in some of them, something deep and permanent about how they see the world. The mission has already returned value, in the coin of meaning and perspective that is incalculable, and it will continue to do so. As long as human beings, or whatever descendants of human beings exist in the future, are capable of thinking about time and scale and the nature of existence, the story of Voyager 1 will be available to provoke thought and inspire wonder. The spacecraft itself moves further away every second, but the idea of it, the significance of it, travels at the speed of memory, which is to say it does not travel at all. It simply exists in the minds of anyone who has encountered it and been changed by it. Memory is a strange thing when you think about it at the scale of civilizations. Individual memories fade and die with the individuals who hold them, but some memories are passed on, encoded in stories and books and cultural practices, replicated from mind to mind across generations. The memories that survive this replication process are not exactly the same as the original experiences that created them. They are transformed, simplified, enriched with meaning that accretes over time. The stories we tell about historical events are not the same as the events themselves. They are living things, changing as they are told and retold, carrying the emotional weight of all the people who have carried them. The story of Voyager 1 is already one of these living memories. It has been told and retold. It appears in books and documentaries and school curricula. It comes up in conversations about humanity's relationship with the cosmos, about the meaning of exploration, about what we value and why. And because it is a story with no ending, because Voyager 1 is still out there, still moving, it retains a kind of openness that finished stories do not have. It is not a chapter in history. It is an ongoing event, and that quality of ongoingness, of a story that has not yet concluded, gives it a special kind of vitality. In a million years, the story will be very old. The world will have changed in ways we cannot predict. The specific cultural memory of Voyager 1 as it exists today, the names of the scientists who built it, the names of the politicians who funded it, the specific technological context of the late 20th century, all of this will almost certainly have been lost, transformed, or superseded. What might remain, in some form, is the deeper significance, The fact that at a particular point in the development of a technological civilization, that civilization chose to reach beyond its own boundaries and send something of itself into the universe. That is the kind of fact that tends to survive the specifics. It is the shape of the gesture that persists, even when the details of how it was made have been forgotten. This is true of many of the most significant moments in human history. We remember that someone sailed west and encountered an unknown continent. We do not all carry in our minds the specific navigational details or the precise provisions on the ships. We remember that someone first split the atom. We do not all understand the specific mathematics of nuclear fission. The significance persists even when the technical details fade. And the significance of Voyager 1 is this: we reached beyond our own solar system for the first time, and we put something of ourselves in the reaching. A small golden disk carrying the sounds of home, moving through a universe that is older and larger and more indifferent than we can fully imagine. That gesture, that reaching, is perhaps the most important thing humanity has ever done in space. Not because of the science it returned, which was genuinely significant, not because of the engineering challenge it represented, which was formidable, but because it was the first time we extended ourselves beyond the solar system, the first time we placed something of our civilization in interstellar space, the first time we made a mark, however small, on the galaxy. And that mark, moving now at 17 kilometers per second through the interstellar medium, will persist long after every other monument we have built. Every pyramid and cathedral and skyscraper and satellite has crumbled or decayed or been swallowed by time. The legacy of Voyager 1 is not primarily scientific, it is philosophical. It is the demonstration, achieved in hardware rather than in words, that the universe is something we are willing to address, that we do not merely look at the night sky and wonder, that we make things and send them and hope, even without guarantee, that the sending matters, that we are at our best a species that leans toward the horizon rather than away from it. And that quality, that leaning, is something worth remembering, however the future chooses to do the remembering. We have come a long way together in this story. We started with a simple question: where will Voyager 1 be in 1,000,000 years? And we have spent these chapters slowly approaching the answer, circling it from different angles, letting the scale and the context and the meaning accumulate before arriving at the number. Now it is time to give the answer clearly, and then to say something about what the answer means and why the question was worth asking in the first place. In 1,000,000 years, Voyager 1 will be approximately 40 to 60 light years from Earth. The most central estimate is around 50 light years, though the exact figure depends on the gravitational perturbations of stellar encounters along the way, which introduce some uncertainty into the calculation. The spacecraft will be located in the general direction of the constellation Ophiuchus as seen from Earth today, though the stars in Ophiuchus will have shifted from their current positions by then, and the constellation itself will look quite different from how it does now. Voyager will still be inside the Milky Way galaxy, well within the Orion Arm, the spiral arm structure that contains our solar system. It will have passed through the Oort cloud, emerged into truly interstellar space, had a moderately close encounter with the star Gliese 445, and continued on its way. The spacecraft will be completely silent by then. Its power source will have been exhausted for hundreds of thousands of years. Its instruments will have been dark for just as long. Its transmitter will be producing no signal. It will be, from an engineering standpoint, a dead machine. But it will be physically intact, or close to it. The structural metals, the gold-plated copper of the Golden Record, the basic geometry of the dish antenna and the science booms, all of this will still be recognizably Voyager 1, slightly pitted by interstellar dust, faded in color from cosmic radiation, but present, real, moving. It will be moving at essentially the same speed it is moving today, about 17 kilometers per second relative to the Sun. The small deviations introduced by stellar gravitational encounters over 1,000,000 years will have altered its velocity slightly, but the order of magnitude remains the same. It will be drifting, silently, through a region of interstellar space that no human instrument has ever visited, in the direction of a sky that no human eye has ever seen from, carrying a message that no one has yet read. That is the answer. And it is, when you look at it clearly, both more modest and more profound than the question might have suggested. Modest, because 50 light years is, in the context of a galaxy 100,000 light years across, a tiny distance. The spacecraft has not gone far. By cosmic standards, it has barely moved. Profound, because 50 light-years is also a genuinely extraordinary distance for anything made by human hands to travel, and because the fact of its being there, the fact that something of ours has reached that far and will be there, drifting, for all of the unimaginable time that follows, is a remarkable thing for a young and small species to have achieved. But the answer, clear as it now is, leads directly to a deeper question. And this deeper question is, I think, the one the whole story has been building toward. Not where will Voyager 1 be, but why does it matter where Voyager 1 will be? What does it mean for a civilization to send something into interstellar space? What does the act of reaching, knowing that the reach will not result in arrival, say about the species doing the reaching? These are not rhetorical questions. They are genuine ones, and they deserve genuine engagement. The easy answer is that it matters for the science. Voyager 1 returned enormous amounts of scientific data during its active mission. It transformed our understanding of the outer planets and their moons. It provided the first direct measurements of the interstellar medium. It confirmed the existence and location of the heliopause and helped calibrate our models of how the solar wind interacts with interstellar space. All of this is real and valuable and contributed meaningfully to human knowledge. The scientific case for Voyager 1 is strong, but the scientific case, while strong, does not fully account for why the mission continues to resonate in the way that it does. People who have never heard of a heliopause care about Voyager 1. People who could not name the instruments on board are moved by the image of the pale blue dot. People who do not follow space news closely still feel something when they hear that Voyager 1 is the farthest thing we have ever sent into space. The resonance is not primarily scientific, it is something else. Something harder to name but no less real. What I think it is, after turning the question over for a long time, is this. Voyager 1 represents the best of a particular human impulse, which is the impulse to go beyond the current boundary of the known. This impulse is not unique to space exploration. It drove the first humans to cross land bridges into unknown continents. It drove the first ocean voyages into open water with no sight of land. It drove the first climbers to attempt the highest mountains, not because anyone needed what was on top, but because the top was there and had not yet been reached. It drives the scientific enterprise in general, the constant pushing at the edge of what is understood, not because we always know in advance what we will find, but because the finding is its own justification. Voyager 1 is an expression of this impulse in its purest form. It went not because there was a resource to exploit at the other end, not because there was a strategic advantage to be gained, not because it was economically rational to send it. It went because the solar system had an edge, and we wanted to know what was beyond it. It went because the stars had never been visited by anything we made, and we wanted to try. It went, in a deeply human way, because going was possible and not going would have been a kind of failure of imagination. And the Golden Record is the clearest expression of this impulse within the mission. The record serves no practical navigational or scientific function. It adds cost and weight and complexity without improving the spacecraft's ability to do science. It was included because the scientists who built the mission believed that if you are going to send something into interstellar space, the right thing to do is to introduce yourself. That sending something without saying something would be a missed opportunity, and that saying something without trying to say it as well as you possibly can would be a failure of seriousness. The Golden Record is, above all, an act of seriousness, a recognition that the moment deserves something more than just hardware. In a million years, Voyager 1 will still be out there. It will not know what year it is. It will not know that a million years have passed since it left. Time does not mean anything to a machine that cannot think. The million years will have passed only for us, for Earth, for the universe around the spacecraft, and for whatever descendants of humanity might exist to mark the anniversary. The machine will simply be wherever it is, moving at whatever speed it is moving, carrying whatever it carries. But the significance of the moment will belong entirely to the thinking beings who can appreciate it. And what those thinking beings, if they exist, will be able to say is this. 1 million years ago, on a small rocky planet orbiting an ordinary star in the outer regions of the Milky Way, there were creatures who became aware of themselves and their surroundings and began, with enormous effort and over many generations, to understand the universe they lived in. They were not very old as species go. They were not very powerful as civilizations go. They were full of contradiction and conflict and tremendous difficulty. But they were curious. And their curiosity was genuine enough and bold enough that they decided, at a specific moment in their history, to send something of themselves beyond the edge of everything they knew. They sent a machine. They sent a message. They sent the sounds of rain and music and heartbeats. They sent the voices of people speaking languages that had taken thousands of years to develop. They sent the mathematics of their science and the imagery of their world, and the careful, uncertain hope that someone, somewhere, in some other corner of this vast and largely silent universe, might eventually find it. The machine is still moving. It will be moving in 1,000,000 years, in 10 million, in 1 billion, in some form. It is the farthest thing our kind has ever sent anywhere. And it is also the most honest thing we have ever sent anywhere. Because the honest truth about humanity, underneath all of the power and the conflict and the beauty and the tragedy, is that we want to be known. We want to be understood. We want to believe that our existence, however brief in cosmic terms and however small in cosmic scale, means something. And sometimes, in our best moments, we reach out into the dark to say so. Voyager 1 is that reaching, extended now across more than 24 billion kilometers of space, and growing by 1.5 million kilometers every day, and still going, and will still be going long after every human being alive today has been gone for a very long time. It carries no crew, it carries no weapon, it carries no commercial cargo, it carries music and math and the sound of rain. It carries greetings in 55 languages. It carries an image of a man and a woman standing next to a drawing of the machine that carries the image, somewhere in the interstellar medium, moving silently away from everything they knew. The question we started with was, where will Voyager 1 be in 1,000,000 years? The answer is about 50 light-years from Earth, in the interstellar medium, somewhere in the direction of Ophiuchus, still intact, still carrying its golden record, still moving at 17 kilometers per second. But the question the answer leaves us with is larger and slower and more important. It is the question of what it means to be the kind of creature that asks where something will be in 1,000,000 years. What it means to be able to think about timescales that dwarf your own existence by a factor of hundreds. What it means to build something and send it away, knowing that neither you nor anyone you will ever meet will see where it ends up. The answer to that question is that it means we are alive in a particularly rich way. Not just biologically alive, processing nutrients and reproducing, but alive in the way that requires consciousness and curiosity and the ability to love something for what it represents beyond its immediate usefulness. We are alive in a way that can feel awe at a pale blue dot, that can build a golden record and mean it, that can ask where something will be in 1,000,000 years and care about the answer and be changed, however slightly, by the contemplation. That quality of aliveness is the rarest thing in the universe we have found so far. The universe is vast and old and full of matter and energy, but almost all of it is unconscious. Almost all of it does not know it exists. Almost all of it does not wonder, does not reach, does not feel the pull of the horizon or the weight of the stars. We do. Whatever mistakes we make, whatever destructive tendencies coexist with our curiosity and our compassion, we are the part of the universe that is awake to itself. And Voyager 1 is the farthest that awakeness has ever travelled. So tonight, when the sky is clear, look toward Orion. Look toward the upper part of that familiar constellation, and then let your gaze drift slightly upward and to the left. Somewhere in that general direction, though far too far and far too small to see, there is a machine we made. It is moving away from you at 17 kilometers per second. It has been moving for almost 50 years. It will be moving for 1,000,000 years from now, and long after that, in the quiet dark between the stars, carrying a small golden disc that says, in 55 languages, and in music, and in mathematics, and in the sounds of rain, we were here. We thought about you. We hoped you would hear this. The answer to where Voyager 1 will be in 1,000,000 years is 50 light-years from Earth. But the answer that matters is, further than we could reach any other way, in the most generous direction possible, carrying the most hopeful version of ourselves we were capable of putting together. That is where it will be. That is where it will always be. Moving, reaching, going.